All right, so today we're going to look at part 2 of section 3.2. We're going to be looking at domain and range of log functions and then graphing them. But first, let's look at what's the domain and range. Remember, exponentials and logs are inverse functions, and we know by definition of inverse functions that the domain and range exchange places. So if I'm looking at the domain of my exponential function, that would be all real numbers. Well, if they're inverse functions, then the range of a log would have to be all real numbers. If my range of here is y is greater than 0, my domain, which are my x's, would have to be x greater than or equal to 0, which only makes sense because I cannot take the log of a negative number. So let's look at finding domain and range of the following. This is a k-value. Notice it is outside the parentheses, unlike the next example where we have parentheses around something. So here, my domain, x is greater than 0. My range, all real numbers. In this example, this whole thing, x minus 1 has to be greater than 0. So x is greater than 0. And my range is all real numbers. What about this one? Same idea. My domain, x plus 2, has to be greater than 0 because I cannot take the log of a negative. So my domain would be defined as x is greater than negative 2, while my range is all real numbers. So another one. Again, my domain has to be 2x minus 5 greater than 0. So x has to be greater than 5 halves. And my range, all real numbers. Oops, I should be distant R. And last but not least, again, same thing. 5x plus 2 has to be greater than 0 because I cannot take the log of a negative number. So x is greater than negative 2 halves. My range will be all real numbers. So what does the graph of x, let's look at it, okay? So my inputs were 0 and 1. My outputs were 1 and 2. My asymptote, I had a horizontal asymptote at x at y equal 0. So here's my 2 to the x. That's y equals 0, 0, 1, 1, 2, one like this. So this is y equal 2 to the x. Well, if I'm looking at it, they're reflected. Inverse functions are reflected over the line y equal x. So let's sketch that really quick. 4, 4, yeah, okay, so that's close enough. We know that the domain and range change, so let's switch my domain and range from above. What was my range? My range was 1, 2, so that becomes my domain. My domain was 0, 1, so it becomes my range and my inverse function. So it's 1, 0, 2, 1, and notice this time my asymptote is going to switch. It's now going to become a vertical asymptote of x equals 0. And so my function, okay, is a reflection over the y equal x. Okay, so that's what it's going to look like. They're going to have vertical asymptotes, and it's going to generally be on the other side and not reflective. Generally, it can be. Okay, so how do we do this? First, you want to find the domain. That becomes your vertical asymptote. Then we're going to use the matching bases idea and the base to the 1, two of our properties, to plot the 2 points. Okay, so first let's find our domain. Can't be negative, so x is greater than 0, and our range is all real numbers. The domain defines our vertical asymptote. So my vertical asymptote is at x equal 0. So we're going to have some inputs. In logs, I like to call it inputs and outputs. I need my x to equal the base, and I need my x to equal 1. I need my x to equal the base, and my x to equal 1. Let's start with x equal 1, and x equal my base. Well, if x equals 1, okay, if x equal 1, then log base 3 of 1, that's that property that says it's equal to 0. Log base 3 of 3 is that property that says it's equal to 1. So let's plot these points. X is 1, y is 0. X is 3, y is 1. There's my log graph. Let's do another one. We have several we're going to be doing here. Okay, so again, start with the domain. Let's define it. X is greater than 0. Okay, why is it greater than 0? X plus 1 is not in parentheses. There's a plus 1 at the end. It's not in the parentheses. Range, all real numbers. Again, this will define my vertical asymptote. X equals 0. Now we have to figure our inputs and our outputs. So we want our input, x to equal 1, and x to equal the base. My output, log base 4 of 1 plus 1. Well, log base 4 of 1 is 0. 0 plus 1 is 1. So that's my first input. 1 yields an output of 1. So the point is 1, 1. I'm plugging my log base 4 of 4. Well, what log base 4 of 4 is equal to 1. 1 plus 1 is equal to 2. So my other point is 4, 2. Plot that. Connect the dots. And we're done with our log graph. Let's look at another one. Now we have log base 4, x plus 1. Notice the x plus 1 is in parentheses, which is different from the previous problem. So what I'm going to say is my domain then is x plus 1 is greater than 0. So x is greater than negative 1. Range, all real numbers. This defines my vertical asymptote. Vertical asymptote is at x equals negative 1. Now this is where I say inputs and outputs, because I want my input, that x plus 1, my log x plus 1 to equal 1, and I want my other input for x plus 1 to equal the base, which is 4. So now I have to solve for x. What is the actual x value I need? Subtract 1. So the actual x value I need is x, and this is why. Let's look at this. Log base 4, x is 0, right there, plus 1. Log base 4 of 1 is equal to 0. So I can use my identities, my properties that I have. Subtract 1, my x is equal to 3. So if I go log base 4 of 3 plus 1, that's log base 4 of 4. I'm using my property now that the log base 4 of 4 is equal to 1. So let's plot our points. 0, 0, 3, 1. Okay, now let's put it all together where I have everything there. Okay, where I have everything. All right, so let's look at this. Domain. X minus 3 greater than 0. X greater than 3. Range, all real numbers. Okay, again, this defines my vertical asymptote, so x is equal to 3. So we're inputs and outputs. I want that x minus 3 to equal 1. And I want my x minus 3 to equal the base, which is 2. So add 3. So here my x is equal to 4. Add 3. X is equal to 5. Let's substitute it into our logs. So log base 2, I said x is 4. And then I have a plus 2 out here. Log base 2 of 1 plus 2. Well, log base 2 of 1 is 0 plus 2 equals 2. So this is my point. 4, 2. I'm going to go ahead and put that on the graph now. 4, 2. Let's do it again for 5. Log base 2 of 2 plus 2. Well, we know from our property that this is equal to 1. And I have a plus 2, so it's 3. So the point is 5, 3. And then there's my graph. 2 more. It starts exactly the same way every time again. So we're going to look at our domain. X plus 7 greater than 0. So x is greater than negative 7. Range, all real numbers. Defines my vertical asymptote at x equal negative 7. Put that in. So I'm going to have now my inputs and my outputs. I want x plus 7 to equal 1. And I need x plus 7 to equal the base, 7. Subtract 7 from both sides, x equal negative 6. Subtract 7, x is going to equal to 0. And let's find my outputs then. Log base 7, negative 6 plus 7 minus 1. Log base 7 of 1 minus 1. Well, we know that this is our property, so that's 0 minus 1 equals negative 1. So my point is negative 6, negative 1. Add closer to negative 2 on that. Let's try that again. Negative 1. Closer right there. Okay, so let's plug in 0. Log base 7, 0 plus 7 minus 1. Log base 7 of 7 minus 1. Well, we know log base 7 of 7 is 1, and 1 minus 1 is equal to 0. So we're at the origin of 0, 0. And here's our log graph. Last one. Start with our domain. Our domain is x is greater than 0. This minus 4 is on the outside, it's not in the parentheses, that's how I know that. Range, all real numbers, so my vertical asymptote is at x equal 0. That's my vertical asymptotes. We go into our inputs and outputs. Okay, so my input, I want x to equal 1. And I want x to equal my base. The base is implied, so x is going to equal 10, implied base. Okay, so first step, log base 10 of 1 minus 4 is 0 minus 4, so that's negative 4. Log base 10 of 10 minus 4. Notice minus 4 is out here. It's not 10 minus 4. It's not 6. Got to be careful with that. Log base 10 of 10 is 1 minus 4 is negative 3. Okay, notice how my graph is scaled by units of 2. So we're at x equal 1, negative 4. Okay, because it's scaled by units of 2. X equal 10, and I'm at negative 3. And that's how you would graph logarithmic graphs.